Hello, today guys, we're going to talk about free fall. And free fall is when any object is dropped in the presence of gravity. Now, for the most part, we're going to focus on Earth's gravity, but this could be any gravity. We could be talking about Mars's gravity or anything. Now, we're going to have different values though, because those planets have different gravitational fields. Here on Earth though, ours is pretty well explored, and your reference table is going to tell you the most important thing about this. But let's start off here first. The important thing to know, guys, is that your VI for all freefall, no matter what planet you're on, is 0 meters per second. And you can see this right here. This is what the first time, once she lets the ball go, it's initially at rest. And this diagram, I like it. It simplifies, but it says at time 1 it's going, or at time 0 it's going 0 meters per second. At time 1 it's going 10 meters per second. At time 2 it's going 20. Time 3 it's going 30. Time 4 it's going 40. Time 5 it's going 50. Now this is not exactly 100% accurate. And if you take a look at your New York State's physics table, you'll see that we go down, up, acceleration due to gravity right there. And that's going to be g, often just symbolizes g, and we're not actually going to use 10. A lot of times you'll see it's abbreviated as 10 meters per second squared, but we're actually going to have to use, because of New York State, 9.81 meters per second squared. But this is what you use in college, and this is actually what Mr. Shaw used in Ohio. So let's go back. So here we go, and notice, guys, once again, for every second it falls, it's going to gain 10 meters per second. Let's actually use Excel to do this, guys. Now, Excel is a great program, and if you use Excel properly, it's going to do your homework really just for you. So let's make a time be our first one. Okay, we'll go 0 and 1. We're going to expand in a second. And now, the next one, let's just make that D. Enter. And, okay, we'll come back to that. Well, actually, no. I'm going to change it just for 1 second. Let's grab these and move these over. Okay, now the one thing I want to remind us, guys, our VI is always going to be 0. No matter what, we can never change within the initial conditions of an experiment. So your initial conditions of this experiment for any free fall is always going to be 0. Now, we're going to also realize that we are on the Earth. And we are going to be going the acceleration due to gravity from your reference table again. Let me go back and look. Oh, it's 9.81 meters per second squared. So my g is going to be 9.81. I'm going to put it in there twice, and once you get some experience at Excel, you'll see why. Now remember, guys, D, we have a formula for D, and let's go back and we'll look at this blank doc. We should know from our reference table. Actually, I can find it on the reference table. That's a great idea, Andy. I'm going to go back. We can find D, and hopefully you guys did this the other day during the Do Now, that you use this formula right here for your D. We're actually going to see, because I don't want it to come back, we're going to use this formula right here for velocity. This is our distance formula. Okay, good. We'll come back to this though. Don't worry. You don't have to memorize it. Maybe write it down. D equals VI. Now I'm just going to put my VI right here. There's my VI. Plus 0.5 times. Now it's very interesting. Excel uses this as its multiplication thing. It's not x. X will confuse it. Times the acceleration times time and squared. So I can just put times time again. Okay. There it is. 0. And now I'm going to use velocity. Now I'm going to go back and look at my VF formula. Now this is actually not VF. It's going to be instantaneous. If you have questions over this, guys, please make sure I answer them for you. And your V is going to be this formula right here. VF equals VI plus AT. VF equals VI plus A times T. And if you ever want to go back and change any of these, let's hit enter. We can go to this one. You'll see the formula is still up here. You can go to this one and see the formula is still up here. Okay, let's drag these down and let's start to see the magic of Excel. So if I just click on this corner down here, I can pull it up and pull it down. And there you go. It does all the math for me. I don't have to really even, once I've got my formulas in correctly, I don't have to do anything crazy. And you can see when we go back and look at with when we look at this particular one, we'll see that Excel gave us very, very close answers to it, where the person, whoever made this diagram, they said, well, it's going to be 0, 10, 20, 30, 40, 50. We got 9.81. 19.62, 29.43, and so on. So as you can see, their estimation is pretty close, but it's not exactly true. And obviously, if you used 10 meters per second squared, like they did here, you would get a different answer in the end to some extent, small amount. Now let's actually graph this. Let's see if I can do this. I want to put this over here so I can see it. And bring my graph back up. So I've got my VFs and my Ds over here. And let's go to the graphing section. And maybe I can make this a little smaller. And I can bring it over. There we go. So let's make a D versus T graph. Okay, let's do it. Let's go on the very bottom so I can have an edge. So I've got my D, that's in meters, and I've got my T, and that's in seconds. So as you can see, I have a point. Let's go 0, 1, 2. No, I'm making a mistake. Not being sloppy. 0, 1, 2, 3, 4, 5. And these are just going to be ones over here. So I'm just going to go. Well, actually, let's make them tens. Let's go 10. I mean, we're going to be lazy like the people who made that. 20, 30, 40, 50. Okay, I don't think I'm going to. Well, we'll go up to 60. 60, 70, 80, 90. Okay, that's good. Now, we start off, this is our distance versus time graph. We start off at 5 and 1. We're right there. And then we go 19 and 2. I'm doing my distance one over here, guys. 19 and 2. That's about 20. I'm just going to be some rough estimation, guys. Sorry, this is going to be so ugly. You're going to have 44 and 3. It's about right about here. And then we're going to have, let's make this a little bigger. Okay, and then we're going to have 78 and 4, it looks like. And I think we're going to run out of space after that. So we're not going to fit in 5. But you should see this, guys, that this is going to be an exponential curve. Okay, very good. So now we see, guys, that we have, if I zoom in on this, that for displacement we have an exponential curve. So that's how it's going to look for your displacement. And if we think about it, guys, we should know what our velocity is going to look like. Our velocity, let's just delete this. And let's say that this is now velocity. Remember, our velocity, this is a uniform acceleration problem. Hopefully I stressed that enough. This is a uniform acceleration problem. So when you do this, you should be gaining the same velocity each time. So when we do it at 1 second, you should have roughly 10. Next second, you should roughly have 20. The following second, you should roughly have 30. And the following second, you should roughly have 40. And you should see that this is going to be quite linear. So, and that's what it's going to look like, the D versus T graph and the V versus T graph for free fall. Okay, now for your problems. I know this is what you guys want. Free fall. How fast is an object traveling after experiencing free fall for, and we're going to say 30.5 seconds. This will be number 1. Number 2, 44.3 seconds. And number 3, let's go with 60.7 seconds. Okay. So, how fast would the object be traveling after experiencing free fall for this amount of time? Now, remember, guys, this is uniform. I just want to stress this. This is uniform. Uniform acceleration with vi equal to 0 and your acceleration equal to g, which equals 9.81 meters per second squared. Okay, thank you.